Here we have a problem on iterated integrals. Okay, let's go to the information. Combine the sum of the two iterated integrals into a single iterated integral by converting to polar coordinates. Evaluate the resulting iterated integral. Okay, now to combine the given two iterated integrals, first we have to look at the limits of x and limits of y and identify the region bounded. Okay, so first let me take the first iterated integral. So here the outside integral is being evaluated with respect to x and the inside integral is being evaluated with respect to y. Since the outside integral is being evaluated with respect to x, these are the limits we have for x, that is x equals to 0 to x equals to 2. Okay, when I look at the outside integral of the second iterated integral, so like it's 2 to square root of 2, that is it's being evaluated with respect to the same variable x. So that is we have the limits for x, that is 2 to square root of 2. So already we have 2 over here, x equals to 2 to x equals to 2 times square root of 2. So here the starting value of x is 0, the ending value of x is 2 times square root of 2. So usually the distance from 0 to this value represents the radius of a circle. Okay, anyways, now let's go to the limits of y. Okay, when it comes to the first iterated integral, so the inside integral is being evaluated with respect to the variable y. So these are the limits we have for y. Then we have y equals to 0 to y equals to x in the first iterated integral. So when I go over the second iterated integral, the inside integral is being evaluated with respect to the variable y. So we have the limits for y over here, 0 to square root of 8 negative x square. So y equals to 0 to y equals to square root of 8 negative x square. Okay, here we don't have any trouble with the limits of x because it clearly we have the values of x from 0 to 2 times square root of 2. On the x-axis we have to start from x equals to 0, that is origin, to 2 times square root of 2 on the positive side of x-axis. Okay, so here on the y-axis, when I consider the limits of y, we have y equals to 0 to y equals to x. So here we have to sketch graph for this one. Actually, it's a linear equation with the slope 1 and so the y coordinate of the y-intercept is 0. That is when I try to write this equation in the form y equals to mx positive b. So the the coefficient of x over here is 1, the slope is 1 and there is no b value over here. So that means b represents a y coordinate of the y-intercept. Actually, since the b is not there, we can assume there is 0 over here. That means the y coordinate of the y-intercept is 0. So that is this line is passing through the origin 0, comma 0 with the slope positive 1. Okay, now we can sketch the graph of this one, and the graph for this one is just x-axis, because whenever y equals to 0, it represents x-axis, and the same thing here y is equal to 0, it represents x-axis, and we have to be knowing what type of graph do we get for this one. Okay, so for that what I have to do is I have to square both sides. When I square both sides, I'm getting y square equals to 8 negative x square, because when I square this stuff, square it will cancel out. And now when I add x square to both sides, I'm getting x square positive y square equals to 8. And so here clearly we have the equation for circle with center 0, comma 0. The radius r square equals to 8 because it's r square. So when I solve for r, I'm getting 2 times the square root of 2. That is by taking square root on both sides, I'm getting r equals to 2 times square root of 2. So here this is a graph of a circle with center 0, comma 0 and radius 2 times square root of 2. Okay, so already we have the limits for x. It is x equals to 0 to 2 times square root of 2. On the x-axis, I have to mark these values. And so for with the limits of y, we have to sketch the graph of this line y equals to x. And for this one, we have to sketch the graph of a circle with 0, comma 0 as center and radius 2 times square root of 2. And for this one, we have x-axis because y is equal to 0. So when I sketch all this stuff, I'll be getting the region bounded by this by the limits of x and y. Okay, first let me sketch a circle, just a moment. Okay, so here, I've sketched a circle, and let me say this is 1, this is 2, and here 2 times square root of 2, it's very close to 3. Okay, so x values, we have the range of x values from 0 to 2 times square root of 2. That represents the radius of the circle, and the same radius we have here. And so we have to sketch the graph of this line y equals to x. Let me do it 1 second. So y equals to x. It has to pass through the origin with slope of 1 unit. So since the slope is positive, it has to be a rising line. Okay, now just consider the x equals to 0 to x equals to 2 times square root of 2, and this y equals to 0, y is equal to 0 represents the x-axis over here. And this represents a circle with center 0, comma 0 and radius 2 times square root of 2. So this is given over here. So clearly this is the region bounded over here. Okay, so for this region, what is the radius? Actually, this is a sector because it's a part of the circle. So, what is the radius and what is the central angle over here? So, we know that the radius is going to be r is equal to 0 to r is equal to 2 times square root of 2. And here theta is equal to 0 here. And what is the value, angle measure theta over here? So, for that, we have to measure the angle between this line y is equal to x and x-axis over here. So what do we have to do for that? Let's consider, actually this is a, one second, this is the equation of line y equals to x. Now to get the angle measure over here between this line y equals to x and x-axis, so what I'm going to do is I'm going to consider the equation of the line y equals to x. So we have y equals to x. Since we are going to convert this one to polar coordinates, we can use the polar stuff for y and x. We know that y is equal to r, x equals to r cosine theta, y is equal to r sine theta. So we get r sine theta equals to and x equals to r cosine theta. Okay, so now I divide both sides by r, then r will cancel. Here r will cancel. I'm getting sine theta equals to cosine theta. Then I divide both sides by cosine theta. So when I do so, this cosine theta will cancel out. Sine theta or cosine theta is tangent theta using trigonometric identity. So now we have to get the angle measure theta for which the value of tangent is 1. So usually the tangent theta equals to 1 in the first quadrant because the region bounded is in the first quadrant. So like in first quadrant, when tangent theta is equal to 1, theta is equal to pi over 4. So I got pi over 4 here. So now I got the limits for r and theta because we are going to convert this one to polar coordinates. Whenever I convert the given iterated integral to polar coordinates, I have to get the limits for the r and theta. So the limit for r is going to be 0 less than or equal to r less than or equal to 2 times square root of 2. And the limits for theta is theta less than, sorry, not theta, it's the starting value of theta is 0, 0 less than or equal to theta less than or equal to pi over 4. Okay, using these limits, I have to set up the integral which combines the given two iterated integrals. Okay, now let me erase the stuff over here and write the combined integral for the two iterated integrals over here. Okay, let me erase the stuff. Okay, now let me write the combined integral for the given sum of the two iterated integrals using by converting to polar coordinates. Okay, when I convert the given variables to polar coordinates, so instead of x and y, I must have r and theta. So like when I write the combined iterated integral for the sum of the given two iterated integral, the first integral has to be written with the limits of theta. So already we have the limits of theta over here, that is 0 to pi over 4. And the second integral must be written with the limits of r. So the limits of r is 0 to 2 times square root of 2 in this region. Okay, now so we have to write that is so whatever stuff we have here, it has to be converted to polar coordinates. Already we know that so here x square positive y square equals to r square. So when I take r square, when I take square root on both sides, I'm getting square root of x square positive y square equals to square root of r square. So then square root of r square is just r. So the square root of x square positive y square equals to r because here the square root and square will cancel out. Okay, now let me write instead of the square root of x square positive y square over here, I have to write r. And already we know that so whenever I convert the given iterated integral to polar coordinates, so what I have to do is I have to for dy and dx, I have to write r times dr d theta. So we can replace this dy over dx in the given two integrals. We can write r times dr times d theta. Okay, now the inside integral has to be evaluated with respect to r. So before that 0 to pi over 4 in times 0 to 2 times square root of 2. R times r is r square times dr times d theta. Okay, now let's evaluate the inside integral with respect to r. So let me write 0 to pi over 4. So when I integrate this r square, it will be r to the third power over 3. So 0 to 2 square root of 2. Okay, now let me erase the stuff over here so that I'll find enough space to work on it. Okay, let me continue over here. Integral 0 to pi over 4. Now in the result over here, I have to plug in the upper limit for r. That is, I have to plug in this 2 times square root of 2 for r over here. Let me do it. Then I'm getting 2 times square root of 2 the whole cube over 3 negative. So for the same result, I have to plug in the lower limit 0 for r over here. When I plug in 0 for r over here, is 0 cube is 0. 0 divided by anything is 0. So 0 times d theta equals to integral 0 to pi over 4. So now here two values are multiplied and we have the common exponent 3. So whenever two values are multiplied and we have the common exponent, the exponent can be distributed to each value and multiply the results. Then I'm getting 2 cube times square root of 2 the whole cube over 3, and we can ignore this 0 and we have to write d theta, then integral 0 to pi over 4. The evaluation of this 2 cube is just 8. Now if I evaluate this square root of 2 whole cube, I'm getting, let me write the stuff over here. To evaluate this square root of 2 the whole cube, what I have to do is I have to multiply the square root of 2 by itself for 3 times, because we have square root of 2 whole cube. When I multiply square root of 2 and square root of 2, I'm just getting 2, and we get 2 times square root of 2. So the evaluation of this square root of 2 the whole cube is 2 times square root of 2. So let me write it over here. So times 2 times square root of 2 over 3 times d theta. Let me continue the stuff over here. So integral 0 to pi over 4. So 8 times 2 is 16, then 16 square root of 2 over 3 times d theta. Okay, actually it is a constant. So since it's a constant, it can be moved out of the integral. Then we get 16 times square root of 2 over 3 times integral 0 to pi over 4 d theta. So 16 times square root of 2 over 3. When I evaluate this, when I evaluate the integral of d theta, it will just become theta. And for this theta, we have to take the limits 0 to pi over 4. So now 16 times square root of 2 over 3 times, now for this theta we have to plug in the upper limit pi over 4 negative, and we have to plug in the lower limit 0. So we get 16 times square root of 2 over 3 times. So pi over 4 negative 0 is just pi over 4. 4 goes into 4 one times, 4 goes into 16 4 times. So we get 4 times square root of 2 times pi, that is 4 square root of 2 pi over 3. So I combined the two given iterated integrals and also evaluated the resulting iterated integral. Its evaluation is 4 times square root of 2 times pi divided by 3.